Hello, in this lecture we will answer on two questions. In the first question, we find out the area of this trapezoid ABCD that blocks this circle. In the second question, we find out the area of the green shape, this green shape that is inside rectangle ABCD. So we'll start with the first question. So in the drawing we have a circle that is inscribed by this trapezoid ABCD. In addition, we know that side AB of trapezoid ABCD equals to x units in its length, side DC equals to 7 over x units in its length. This is angle BAD, that is a right angle, and this is angle ADC, that is also a right angle. Again, our mission is to find out the area of this trapezoid ABCD. So, first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. Repeat again. A trapezoid is a quadrilateral with one pair of parallel sides. So here, this is trapezoid ABCD. This trapezoid ABCD, side DC is parallel to the opposite side AB. And for that reason, this quadrilateral ABCD is defined as a trapezoid. The two parallel sides, that is to say DC and AB, are defined as the bases of this trapezoid. And if we define the length of DC as A and the length of AB as B, then the area of this trapezoid ABCD will be equal to the sum of its two bases, that is to say A plus B, times the height, that is h over 2. So the area of this trapezoid ABCD equals to A plus B times h over 2. The height, that is h, must create 90 degrees with the two bases. Here, the height h creates 90 degrees with the base DC, and it is also creates 90 degrees with the base AB. This angle equals to 90 degrees, and this angle equals to 90 degrees. So repeat again, that the area of trapezoid ABCD equals to the sum of its two bases, that is to say A plus B, times the height, that is h, over 2. Okay? The area equals to A plus B times h over 2. So, first of all, we will define the point of tendencies of this trapezoid ABCD with this circle with letters. We will define the point of tendency of tangent AB with this circle, this point, as E. Likewise, we will define the point of tendency of tangent AD with this circle, this point, as F. We define the point of tendency of tangent BC with this circle, this point, as G. And finally, we define the point of tendency of tangent DC with this circle, this point, as we define this point as H. So here we can implement rule 2. Repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common extra point to a circle are equal. So in the drawing we have a circle. This is the common extra point, point P. From this common extra point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, their lengths are equal to each other. That is to say, PA equals to PB. You can actually implement rule 2 in our drawing. Why? Because in our drawing, if we focus on this common external point A, from this common external point A, we have two tangents to this circle, tangent AE and tangent AF. And according to rule 2, they are equal to each other. That is to say AE equals to AF. So if we define the length of this tangent AE as y, then the length of tangent AF must be also equal to y according to rule 2. Likewise, we focus on this common external point V. From this common external point V, we have two tangents to this circle, tangent BE and tangent BG. And according to rule 2, they are equal to each other. That is to say, BE equals to BG. So if we define the length of this tangent BE as Z, then the length of this tangent BG must be also equal to Z according to rule 2. Likewise, we will focus on this common external point C. From this common external point C, we have two tangents to this circle, tangent CG and tangent CH. And according to rule 2, they are equal to each other. That is to say, CG equals to CH. So, if we define the length of this tangent CG as M, then the length of this tangent CH must be also equal to M according to rule 2. And finally, we focus on this common external point D. From this common external point D, we have two tangents to this circle, tangent TH and tangent DF. And according to rule 2, they are equal to each other. That is to say, DH equals to DF. So if we define the length of this tangent DF as T, then the length of this tangent DH must be also equal to T according to rule 2. In the next step, we define the length of side AD of this trapezoid ABCD as A. So AD, this is side AD, and it is equal to A according to our definition. Likewise, we define the length of this side BC of trapezoid ABCD as B. That is to say, the length of this tangent of this side BC of trapezoid ABCD equals to B units. In the next step, we will add side AB to the opposite side DC. So what is the value of AB plus DC? AB plus DC AB, according to rule 2 actually, is equals to Y plus Z. Okay, AB equals to Y plus Z. Plus DC. So DC according to actually rule 2 is equals to T plus M. So if we found out that in total AB plus DC equals to Y plus Z plus T plus M. Likewise, we join points we join side AD of trapezoid ABCD to the opposite side BC. So what is the value of AD plus BC? According to rule 2, AD equals to Y plus T. While BC according to rule 2 is equals to Z plus M. So in total, AD plus BC equals to y plus t plus z plus m. So here you can change the orders of these variables according to the algebraic identity that a plus b equals to b plus a. Therefore, the value of y plus t plus z plus m will be equal to y plus z plus t plus m. We just change the orders of the letters here. So we found out that AD plus BC equals to y plus z plus t plus m, and AB plus DC also equals to y plus t plus z plus m. So those two expressions, AD plus BC and AB plus BC and AD plus BC, they're both equal to the same third expression, that is to say to y plus z plus t plus m, and therefore they are equal to each other. So you can write down that those two expressions, they are equal to each other. Those two expressions are equal to each other, that is to say AB plus DC equals to AD plus BC. So this is this is equation 1. But according to what is given as the question, side AB of a trapezoid ABCD equals to x units in its length. So we'll substitute AB by x. And side DC, also according to what is given as the question, it is equal to 7 over x units in its length. So we substitute DC by 7 over x. And it is equals to, according to equation 1, it is equals to AD plus BC. AD, according to our definition, equals to A. So we substitute AD by A plus BC. BC, according to our definition, equals to B. So we substitute BC by B. So in total, according to equation 1, we actually found out that x plus 7 over x equals to a plus b. This is according to equation 1. In the next step, we will do a construction. That is to say, from point B, we will do perpendicular on DC. Again, from point B, we will do perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point B inside DC. This point is point S. So actually, by doing this construction, we created a quadrilateral ABSD. This is quadrilateral ABSD. Inside quadrilateral ABSD, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size, because of the simple fact that the sum of the three angles that is 270 degrees plus the size of this fourth angle that is 90 degrees. In total it is equals to 360 degrees. That is the sum of the angles in any quadrilateral. So inside this quadrilateral ABSD we have 4 right angles. And according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrilateral ABSD as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABSD, side AB must be equal to the opposite side DS. But side AB equals to x according to what is given as the expression. Therefore, DS must be also equal to x. Side DS must be also equal to DS. Side DS must be also equal to x units in its length. Again, opposite side DS must be also equal to x units in its length. Likewise, according to the sum rule, in the same rectangle ABSD, side AD must be equal to the opposite side BS. But AD equals to A, according to our definition, therefore BS must be also equal to A. Actually, by doing this construction, we created here triangle, the right triangle BSC. In the right triangle BSC, the hypotenuse BC equals to B, side BS equals to A. So, what is the length of this side SC of the right triangle BSC? From the drawing, it is very easy to see that SC equals to DC minus DS. Again, SC equals to DC minus DS. So I write it down. SC equals to DC minus DS. So SC equals to DC. DC equals to 7 over x units in itself, according to what is given as the equation, minus DS. We just write down found out that DS equals to x. So in total, SC equals to 7 over x minus x. So in the next step, I'll copy this right triangle BSC, this right green triangle BSC in a new page, and we'll implement on this right green triangle BSC the Pythagoras theorem. Here by PT is the evaluation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse PC equals to B, side BS equals to A, and we just right now found out that side SC equals to 7 over x minus x. So actually, this is the right triangle BSC that I covered from the original drawing. According to the Pythagoras theorem, this right triangle BSC, BC square, that is the square of the hypotenuse, equals to bs squared plus sc squared. This is equation 2. So BC is B, therefore BC squared is B squared, and it is equals to BS squared. BS is A, therefore BS squared is A squared, plus SC squared. SC is 7 over x minus x, and therefore SC squared is 7 over x minus x squared. So in conclusion, according to equation 2, we shall find out that B squared equals to a squared plus 7 over x minus x squared. Here we use the algebraic identity that a minus b squared equals to a plus b squared minus 4 times ab. So according to this algebraic identity, if we focus on this expression, so 7 over x minus x squared, and we'll substitute 7 over x by a and x by b, we get that 7 over x minus x squared, according to this algebraic identity, will be equal to 7 over x plus x squared minus 4 times a is 7 over x times b, that is x. So we shall find out that the given expression 7 over x minus x squared, according to this algebraic identity, is equals to 7 over x plus x squared. Here we have minus 4 times x over x is 1, so x will get cancelled. After we cancel x, we'll have to only with minus 4 times 7, that is minus 28. In conclusion, we shall find out that according to equation 2, 7 over x minus x squared equals to 7 over x plus x squared minus 28. This is according to equation 2, while according to equation 1, we have already found out that 7 over x, so here we have again 7 over x minus x squared equals to 7 over x plus x squared minus 28. Therefore, we can substitute 7 over x minus x squared in this equation 2 by 7 over x plus x squared minus 28. We will do it now, and we get that according to equation 2, b squared equals to a squared, and here we have 7 over x minus x squared. And we just now found out that 7 over x minus x squared equals to 7 over x plus x squared minus 28. This is according to equation 2. While according to equation 1, we have already found out that 7 over x plus x equals to a plus b. Again, 7 over x plus x equals to a plus b. Repeat again, according to equation 1, we already found out that 7 over x plus x equals to a plus b. So if 7 over x plus x equals to a plus b, it means that 7 over x plus x squared equals to a plus b squared. Therefore, we substitute 7 over x plus x squared in this equation 2 by a plus b squared. We do it now, and we get that according to this equation 2, b squared equals to a squared, and here we just found out that 7 over x plus x squared equals to a plus b. So we substitute 7 over x plus x squared, but 7 over x plus x squared equals to a plus b squared. Here 7 over x plus x squared equals to a plus b squared. So we substitute 7 over x plus x squared by a plus b squared. And we have to subtract also minus 28. This is according to equation 2. So according to equation 2, we found out that b squared equals to a squared plus a plus b squared minus 28. Here we'll open the brackets. We'll open the brackets on this side of the equation 2, and we get that according to equation 2, b squared equals to a squared, and here we have a plus b squared equals to a squared plus b squared plus 2 times a times b minus 28. So here we have b squared on both sides of the equation, so b squared will get cancelled. After we cancel b squared, in this side of the equation we left with nothing, that is to say 0. And it is equals to a squared plus a squared is 2a squared plus 2ab minus 28. This is according to equation 2. Here we add 28 to this equation 2, and we get that according to equation 2, 0 plus 28 is 28. So 28 equals to 2a squared plus 2ab. So here we will divide this equation 2 by 2. Finally we get that according to equation 2, 28 over 2 is 14, so 14 equals to, here we have 2a squared plus 2ab. So 2a squared over 2 is a squared, and 2ab over 2 is ab. So in conclusion, we found out that according to equation 2, a squared plus ab equals to 14. And according to equation 1, we have already found out that x plus 7 over x equals to a plus b. So we have here 2 equations. Repeat again that our mission is to find out the area of this trapezoid ABCD. So according to the formula that I presented to you in the beginning of the lecture, the area of this trapezoid ABCD is equals to the sum of its 2 bases times the height over 2. And the 2 bases must be parallel to each other. In this trapezoid ABCD, side AD is definitely not parallel to side BC. Now we prove that side AB is parallel to the opposite side DC. Why side AB is parallel to the opposite side DC? Because of the fact that we know that ABSD is a rectangle, and we know that the opposite sides of a rectangle are parallel to each other. So in rectangle ABSD, side AB is parallel to the opposite side DS. So AB is parallel to DS, but DS is part of the straight line DC. DS is part of the straight line DC. Again, here DS is part of the straight line DC, and know that DS is parallel to AB. So if a part of the straight line is parallel to another straight line, then the straight line DC itself must be also parallel to the other straight line, that is AB. So in conclusion, we found out that side DC is parallel to side AB in trapezoid ABCD. And therefore, the two parallel sides are AB and DC in trapezoid ABCD. And therefore, they are the bases of this trapezoid ABCD. And the sum of the two bases is equal to AB plus DC. So the area of trapezoid ABCD is equals to the sum of the two bases of trapezoid ABCD. That's actually AB plus DC times the height over 2. Times the height over 2. Here the height must create 90 degrees with the two bases. Here you can see that side AD, this is side AD of trapezoid ABCD, is indeed creates 90 degrees with the base AB. This angle equals to 90 degrees. And it also creates 90 degrees with the other base, that is DC. And therefore the height is AD. AD over 2. So the area of trapezoid ABCD equals to the sum of the two bases, that is actually AB plus DC, times the height, that is AD over 2. According to what is given as the question, side AB equals to x units in its length plus DC. Side DC equals to 7 over x units in its length. So AB is x and DC is 7 over x multiplied by AD. AD is the height. So AD, according to our definition, equals to A. So AD by A divided by 2. In conclusion, we actually found out that the area of trapezoid ABCD equals to x plus 7 over x times x plus 7 over x times A over 2. But according to equation 1, we have only found out that x plus 7 over x equals to A plus B. Therefore, we substitute x plus 7 over x in this expression by A plus B. So in total, this expression equals to A plus B times A over 2. Here we'll open the brackets of this expression. A times A is A squared plus A times B over 2. But according to, so the area of trapezoid ABCD equals to A squared plus AB over 2. But according to equation 2, A squared plus AB equals to 14. So we substitute A squared plus AB in this expression by 14. So this expression in total will be equal to 14 over 2. 14 over 2 is 7. So in conclusion, we found out that the area of trapezoid ABCD is equals to 7 square units. Repeat again. The area of this trapezoid ABCD is equals to 7 square units. So in the next step, I will present to you the second question. In the second question, our mission is to find out the area of this green shape. So, in the drawing, we have rectangle ABCD. We know that side CB of rectangle ABCD equals to 7 units in its length. In addition, inside this rectangle ABCD, we have, this is line segment CP, that is equals to 4 units in its length. This is line segment PQ, that is equals to 2 units in its length. This is line segment QA, that is equals to 5 units in its length. This is angle CPQ, that is a right angle, and this is angle PQA, that is also a right angle. Our mission is to find out the area of this green shape. So first of all, we join point C and A together by a straight line. And we define the intersection point between diagonal CA of rectangle ABCD with line segment PQ, this point SM. We define the length of this line segment PM as X. It is given us the question that PQ equals to 2 units in its length. So what is the length of line segment MQ? From the drawing it is very easy to see that MQ equals to PQ minus PM. Again, MQ equals to PQ minus PM. I'll write it down. MQ equals to PQ minus PM. So MQ equals to PQ, that is 2. According to what is given us the question, minus PM, that is X, according to our definition. So, in total, we should find out that MQ, this is line segment MQ, that is equals to 2 minus X units in its length. Actually, by doing this construction, we created here 2 vertex angles. Angle AMQ is defined as a vertex angle. Likewise, angle PMC is also defined as a vertex angle. So those 2 angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this vertex angle as theta, then the size of the other vertex angle, this angle, must be also equal to theta, of course. In the next step, we'll focus on this right triangle AQM. On this right triangle AQM, this angle equals to 90 degrees. This angle equals to theta. This angle equals to 90 degrees. Therefore, the first missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees. That is the sum of the angles in any triangle. According to the same logic, if we focus on the right green small triangle PCM, this right green small triangle PCM, this angle equals to theta. This angle equals to 90 degrees. Therefore, the missing third angle must be equal to 90 degrees minus theta. So I write it here also. The missing third angle equals to 90 degrees minus theta. In the next step, we will prove that those 2 right triangles are similar to each other. That is to say, we will prove that the right white triangle AQM is similar to this right green small triangle PMC. So why those two right triangles are similar to each other. Here, the right white triangle AMQ. We prove that it's similar to the right green small triangle PMC. So why those two right angles are similar to each other? First of all, those two angles are defined as vertex angles, therefore they are equal to each other. They are both equal to theta, therefore they are equal to each other. So this is angle AMQ. In the right triangle, the right white triangle AMQ, and it is equal to this angle. This is actually angle PMC. In the right green small triangle PMC. Repeat again. Angle AMQ equals angle AMQ in the right triangle AMQ equals to angle PMC in the right triangle PMC. They are both equal to theta, therefore they are equal to each other. In addition, those two angles, they are both right angles, therefore they are equal to each other. So actually this is angle AQM. In the right triangle AMQ, and it is equal to this angle. This is actually angle MPC in the right triangle PMC, the right green triangle PMC. Repeat again. Angle AQM in the right triangle AMQ equals to angle MPC in the right triangle PMC. They are both equal to 90 degrees, therefore they are equal to each other. And finally, those two angles, they are both equal to 90 degrees minus theta, and therefore they are equal to each other. So this is angle MAQ in the right triangle AMQ, and it is equal to this angle. This is actually angle PCM in the right triangle PMC. Repeat again. Angle MAQ in the right triangle AMQ equals to angle PCM in the right triangle PMC. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually proved that all the three angles in the right white triangle AMQ, this right triangle AMQ, are correspondingly equal to all the three angles in this right small green triangle PMC. Therefore proved actually that those two right angles are similar to each other according to angle similarity rule. So I write it down. We proved that the right white triangle AMQ is similar. This is the sign of similar to the right green small triangle PMC according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. that side PM in the right green small triangle PMC over side QMQ in the right white triangle AQM is equals to side PC in the right green small triangle PMC over side AQ in the right white triangle AMQ. Repeat again. We derive that PM over MQ equals to PC over AQ. PM is X according to our definition, so we substitute PM by X over MQ. We already found out that MQ equals to 2 minus X, so we substitute MQ by 2 minus X, and it is equals to PC. PC is 4 according to what is given as the question over AQ. AQ is 5. So in total we found out that X over 2 minus X equals to 4 over 5. Here we cross multiply this equation and we get that 5x equals to 4 times 2 minus X. So here we'll open the brackets on this side of the equation and we get that 5x equals to 4 times 2 is 8 minus 4x. Here we will add 4x to this equation and we get that 5x plus 4x is 9x. So 9x equals to 8. Here we divide this equation by 9 and finally we get that x equals to 8 over 9 or x equals to 8 ninths. X equals to 8 ninths. Line segment PM is equal to X is equals to 8 ninths. So what is the value of MQ that is 2 minus X? 2 is 18 ninths, therefore 2 minus X is 18 ninths minus X. It is 18 ninths minus X, that is 8 ninths. So in total 2 minus X equals to 18 ninths minus 8 ninths. 18 ninths minus 8 ninths equals to 10 ninths. So we actually found out that in total we concluded that PM equals to 8 ninths and 97MQ equals to 10 ninths. Okay, so in the next step I will copy the line AQPC in a new page and we will analyze this line AQPC. Line segment AQ equals to 5 units in its length. Line segment PQ equals to 2 units in its length. And line segment PC equals to 4 units in its length. This angle AQP is a right angle. And this is angle QPC, that is also a right angle. So actually, this is the line AQPC that I copied from the original drawing. In the next step, we will extend the straight line AQ by straight line. Again, we will extend the straight line AQ by straight line. When you extend the straight line by straight line, the result is a straight line. So this is a straight line. So if we focus on the upper side of this, if we focus on the upper side of this straight line at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3, that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of this straight line at point Q? We have this angle that is 90 degrees plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we'll do a construction. That is to say, from point C, we'll draw perpendicular on the extended AQ. Again, from point C, we'll draw perpendicular on the extended AQ. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We'll define the touching point of the perpendicular from point C in the extended AQ, this point is N. So actually, by doing this construction, we created a quadrilateral PCNQ. Inside this quadrilateral PCNQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle must be equal to 360 degrees in total according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral PCNQ, we have 4 right angles. And according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral PCNQ as a rectangle, because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle PCNQ, side PQ must be equal to the opposite side CN. But PQ is 2, therefore Cn must be also equal to 2. Likewise, according to the sum rule, in the same rectangle PCNQ, side PC must be equal to the opposite side Qn. But PC is 4, therefore Qn must be also equal to 4. In the next step, we join point C and A together by a straight line. By joining points A and C, created the right triangle ACN. In the next step, we'll implement the Pythagoras theorem on this right triangle ACN. Here by PT is the variation from Pythagoras theorem. According to the Pythagoras theorem, in this right triangle ACN, AC squared equals to CN squared plus AN squared. So AC squared equals to Cn squared. Cn is 2, therefore Cn squared is 2 squared, that is 4, plus An squared. An in total equals to 5 plus 4, that is 9. Again, An equals to 9, and therefore An squared is 9 squared, that is 81. So in total, we actually found out that AC squared equals to 4 plus 81, that is 85. AC squared, that is the square of the hypotenuse of the right triangle ACN, equals to 85. It is given us in the question that ABCD is a rectangle. And we know that all the angles inside any rectangle are right angles. And therefore, angle ABC, this is angle ABC, that is a right angle. In the next step, I'll copy the right big triangle ABC in a new page, and we will implement on this right big triangle ABC the Pythagoras theorem. side CB equals to 7 units in its length, according to what is given in the question. And we just write down found out that AC squared, that is the square of the hypotenuse of the right triangle ABC, equals to 85. Again, by PT is a version for Pythagoras theorem. So actually, this is the right triangle ABC, this is the common from the original drawing. According to the Pythagoras theorem in this right triangle ABC, AC squared equals to AB squared plus CB squared. Again, here AC squared equals to 85. So we substitute AC squared by 85. And this equals to AB squared. AB is the missing side, so we leave it as it is. So it is AB squared plus CB squared. CB is 7, therefore CB squared is 7 squared, that is 49. We found out that 85 equals to AB squared plus 49. Here we subtract 49 from this equation, and finally we get that AB squared equals to 85 minus 49 is 36. So AB squared equals to 36. Here we take a root out of this equation, and finally we get that AB equals to the square root of 36, that is 6. So we found out that AB, this is side AB, is equals to 6 units in its length. Our mission is to find out the area of this green shape. So what is the area of the green shape? The area of the green shape this green shape equals to the area of the big right triangle ABC. It is equal to the area of the big right triangle ABC. But because of the fact that the area of the big right triangle ABC consists also the area of the right triangle AMQ, we have to subtract from the area of the big right triangle ABC the area of the right triangle AQM, because we are interested only on the green area. So we subtract from the area of triangle ABC the area of the white triangle AQM, and because of the fact that the area of the small white triangle PCM, this area is not included in the area of the big triangle ABC, we have to add to the area of the big triangle ABC, the area of this small white green triangle PMC, because it is not included in the area of triangle ABC. So we add the area of the small white green triangle PMC. So in conclusion, we found out that the area of the green shape equals to the area of the big triangle ABC minus the area of the white right triangle AQM plus the area of the green right small triangle PMC. And again, the area of the green shape in total equals to the area of the big right triangle ABC minus the area of the white right triangle AQM plus the area of the green small triangle PMC. What is the area of the big right triangle ABC? The area of the big right triangle ABC equals to the base of the triangle that is AB times the height that is CB over 2. Repeat again, the area of the big right triangle ABC equals to the base that is AB times the height that is CB over 2. Minus the area of the white triangle AQM. The area of this white triangle AQM equals to the base that is AM and the base that is AQ. This is the base AQ times the height that is QM. This is the height. Why? Because of the fact that QM creates 90 degrees with the base AQ. Therefore, QM is the height over 2. So in total, we found out that the area of the white right triangle AQM equals to the base AQ times the height that is QM over 2. We have to add the area of the white green small triangle PMC. The area of this white small right triangle PMC, the white small green right triangle PMC, it is equals to the base that is PC times the height that is PM. The height is PM because it creates 90 degrees with the base PC. This again equals to 90 degrees. So the area of the right green small triangle PMC equals to the base that is PC times the height that is PM over 2. So the area of the green shape equals to the area of the right triangle ABC. And the area of the right triangle ABC equals to AB 6 times CB 7 over 2. So in total, the area of the right big triangle ABC equals to 6 times 7 over 2 minus the area of the white right triangle AQM. The area of the white right triangle AQM equals to AQ is 5 times QM. QM is 10 nines. This is QM equals to 10 nines over 2. So in total, we found out that the area of the white right triangle AQM equals to 5 times 10 over 2 times 9 plus the area of the right green small triangle PMC. The area of the right green small triangle PMC equals to PC that is 4 times MC that is 8 nines over 2. So in total, we found out that the area of the green right small triangle PMC equals to 4 times 8 over 2 times 9. So the area of the green shape in total equals to the area of the right triangle ABC is 6 times 7 over 2. 6 times 7 is 42 and 42 over 2 is 21. So the area of the right big triangle ABC is 21 square units minus the area of the right triangle AQM. That is equals to this expression. Here 10 over 9 is 5 and 5 times 5 is 25. So in total this expression equals to minus 25 over 9 plus the area of the green small right triangle PMC. That is equals to this expression. 4 times 9 over 2 times 2 over 2 times 9. 8 over 2 is 4 and 4 times 4 is 16. So in total this expression equals to 16 over 9. So the area of the green shape equals to 21, and here we have minus 25 plus 16 is minus 9. So in total, we have here minus 9 over 9. Minus 9 over 9 is minus 1. So in total, the area of the green shape equals to 21 minus 1, that is 20. So we actually found out that the area of the green shape is equal to 20 square units. Repeat again, the area of this green shape is equal to 20 square units. In the next step, I'll summarize the lecture. We start with the first question. The first question, our mission is to find out the area of this trapezoid ABCD. So in the drawing, we have a circle that is inscribed by this trapezoid ABCD. In addition, we know that side AB of trapezoid ABCD equals to x units in itself. This is side DC, this equals to 7 over x units in itself. This is angle A, this is angle BAD, that is a right angle, and this is angle ADC, that is also a right angle. Again, our mission is to find out the area of this trapezoid ABCD. So, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. Repeat again. A trapezoid is a quadrilateral with one pair of parallel sides. So here we have trapezoid ABCD. Side DC is parallel to the opposite side AB. The two parallel sides are defined as the bases of the trapezoid. So DC is the first base and AB is the second base of this trapezoid ABCD. According to our definition, the base DC equals to A and the base AB equals to B. So the area of this trapezoid ABCD equals to the sum of its two bases, that is to say A plus B, times the height, that is H, over 2. Repeat again, the area of this trapezoid ABCD equals to the sum of the two bases, that is A plus B, times the height, that is H, over 2. The height must create 90 degrees with the two bases. Here the height H creates 90 degrees with the base DC, and it also creates 90 degrees with the other base AB. This angle equals 90 degrees and this angle equals 90 degrees. So in total, we found out that the area of trapezoid ABCD equals to the sum of its two bases, that is A plus B, times the height, that is H over 2. Okay. In the first step, we defined the point of tendencies of this trapezoid ABCD with this circle with letters. We defined the point of tendency of tangent AB with this circle, this point as E. We defined the point of tendency of tangent AD or side AD with this circle as F. We defined the point of tendency of tangent BC or side BC of this trapezoid ABCD with this circle, this point as G, and finally we defined the point of tendency of tangent DC with this circle, this point as H. So here we can implement rule 2. According to rule 2, the length of two tangents from a common external point to a circle are equal. So in the drawing we have this circle and the common external point P. From this common external point P we have two tangents to this circle. The red tangent PA and the blue tangent PB. And according to rule 2 they are equal to each other. That is to say PA equals to PB. We can definitely implement rule 2 in our drawing. Why? Because if we focus on this common external point A, from this common external point A, we have two tangents to this circle, tangent AE and tangent AF. And according to rule 2, they are equal to each other. That is to say, AE equals to AF. So if we define the length of this tangent AE as y, then the length of tangent AF must be also equal to y according to rule 2. Likewise, if you focus on this common external point B, from this common external point B, we have two tangents to this circle, tangent BE and tangent BG, and according to rule 2, they are equal to each other. That is to say, BE equals to BG. So if we define the length of BE as Z, then the length of tangent BG must be also equal to Z according to rule 2. So if we focus on this common external point C, from this common external point C, we have two tangents to this circle, tangent CG and tangent CH. And according to rule 2, they are equal to each other. That is to say, CG equals to CH. So if we define the length of tangent CG as M, then the length of this tangent CH must be also equal to M according to rule 2. And finally, if we focus on this common external point D, from this common external point D, we have two tangents to this circle, tangent DF and tangent DH. And according to rule 2, they are equal to each other. That is to say, DF equals to DH. So if we define the length of this tangent DF as T, then the length of tangent DH must be also equal to T according to rule 2. Okay. In the next step, we define the length of this side BC of trapezoid ABCD as B, and we define the length of this side AD as A. And then, what is the value of AB plus DC? AB plus DC according to rule 2, AB equals to Y plus Z. And DC according to rule 2 equals to T plus M. DC equals to T plus M. So in total, AB plus DC equals to Y plus Z plus T plus M. Likewise, what is the value of side AB plus the opposite side BC of trapezoid ABCD? So what is the value of AD plus BC? AD according to rule 2 equals to Y plus T, and BC also according to rule 2 equals to Z plus M. So in total, AD plus BC in total equals to Y plus T plus Z plus M. We can change the orders of the letters in this expression according to the algebraic identity that A plus B equals to B plus A. So instead of Y plus T plus Z plus M, we can write down that this expression equals to Y plus Z plus T plus M. So AD plus BC equals to Y plus Z plus T plus M, and AB plus DC also equals to Y. Again, AD plus BC equals to Y plus Z plus T plus M, and AB plus DC also equals to Y plus Z plus T plus M. So those two expressions in the green color, they are both equal to the same third expression, that is actually Y plus Z plus T plus M, and therefore they are equal to each other. That is to say, AB plus DC equals to AD plus BC. This is actually equation 1. AB, only to what is given as the equation is X. DC is 7 over X. AB is X, DC is 7 over X. AD is A and BC is B according to our definition. So in conclusion, we actually found out that according to equation 1, X plus 7 over X, X plus 7 over X equals to A plus B. In the next step, we did a construction. That is to say, from point B, we draw perpendicular on DC. Again, from point B, we draw perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and DC as point S. By doing this construction, we created here quadrilateral ABSD. Inside this quadrilateral ABSD, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth facing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the fourth missing angle must be equal to 90 degrees in its side. So inside quadrilateral ABSD, we have 4 right angles. And according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrilateral ABSD is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABSD, side AB must be equal to the opposite side DS. But AB is x, therefore ds must be also equal to x. Likewise, according to the sum rule, in the same rectangle ABSD, side AD must be equal to the opposite side BS. But AD is A, according to our definition, therefore BS must be also equal to A. So, by doing this construction, we created here the green right triangle BSC. In the green right triangle BSC, the hypotenuse BS equals to B, side B, the hypotenuse BC, this is the hypotenuse BC that is equal to B, side BC, side BS, this is side BS that is equal to A. So what is the length of side SC? From the drawing, it is very easy to see that SC in total equals to DC minus DS. Again, SC equals to DC minus DS. SC equals to DC minus DS. So SC equals to DC, that is 7 over x, minus DS, that is x. So in total, SC equals to 7 over x minus x. So in the next step, I copied the green right triangle BSC in a new page and implemented the Pythagoras theorem on this green right triangle BSC. So actually, this is the green right triangle BSC that I copied from the original drawing. We just like now found out that side AC equals to 7 over x minus x, BS equals to A, the hypotenuse BC equals to B. So according to the Pythagoras theorem, in this right triangle BSC, BC square equals to BS square plus SC square. BC square equals to BS square plus SC square. BC is B, therefore BC square is B square, and it is equals to BS square. BS is A, therefore BS square is A square, plus SC square. SC is 7 over x minus x, therefore SC square is 7 over x minus x square. Here we use the algebraic identity that A minus B square equals to A plus B square minus 4 times AB. According to this algebraic identity, if we focus on this expression 7 over x minus x square, and we just substitute 7 over x by A and x by B, we will get that 7 over x minus x squared according to this algebraic identity is equals to 7 over x plus x squared minus 4 times 7 over x times x. So here we have x in the numerator and x in the denominator, so x will get cancelled. So in total, this expression, after we cancel x, will be equal to minus 4 times 7, that is minus 28. So in total, 7 over x minus x squared, according to this algebraic identity, will be equal to 7 over x plus x squared minus 28. Therefore, we can substitute 7 over x minus x squared in this equation 2 by 7 over x plus x squared minus 28. We did it and found out that according to this equation 2, b squared equals to a squared, and here 7 over x minus x squared equals to 7 over x plus x squared minus 28. So in total, we found out that according to equation 2, b squared equals to a squared plus 7 over x plus x squared minus 28. And here, according to equation 1, seven over x plus x equals to a plus b, therefore 7 over x plus x squared will be equal to a plus b squared. Therefore, we can substitute 7 over x plus x squared in this equation 2 by a plus b squared. We did it and found out actually that according to equation 2, b squared equals to a squared, and 7 over x plus x squared equals to a plus b squared minus 28. So, according to equation 2, we actually found out that b squared equals to a squared plus ab plus a plus b squared minus 28. Here we open the brackets on this side of this equation 2, and finally found out that b squared equals to a squared, and a plus b squared equals to a squared plus b squared plus 2 times ab minus 28. Here we have b squared on both sides of the equation, so b squared will get cancelled. After we cancel b squared, on this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have a squared plus a squared, that is 2a squared, plus 2ab minus 28. Here we added 28 to this equation 2, and found out actually that 0 plus 28 is 28. On the other side of the equation we have 2a squared plus 2ab. Here we divided this equation 2 by 2, and finally found out that according to equation 2, 28 over 2 is 14, and it is equals to 2a squared over 2 is a squared, plus 2ab over 2 is ab. So in total, according to equation 2, we actually found out that 14 equals to a squared plus ab, while according to equation 1, we have already found out that x plus 7 over x equals to a plus b. Our mission is to find out the area of this trapezoid ABCD. So according to the formula that I presented to you in the beginning of the lecture, the area of this trapezoid ABCD equals to the sum of its two bases times the height over 2. The two bases must be parallel to each other. Here you can see that in trapezoid ABCD, side AB is definitely not parallel to side BC. Now we will prove that side AB is parallel to the opposite side DC in trapezoid ABCD. So why AB is parallel to DC? Because of the fact that we know that ABSD is a rectangle, and we also know that the opposite sides of a rectangle are parallel to each other. So in rectangle ABSD, side AB is parallel to the opposite side DS. But DS is part of the straight line DC and is parallel to AB. So if a part of the straight line is parallel to another straight line, then the straight line DC itself must be also parallel to another straight line, that is AB. So in conclusion, we actually found out that side DC is parallel to side AB, and therefore AB and DC are the bases of trapezoid ABCD. And therefore the sum of the two bases of trapezoid ABCD is equal to AB plus DC. So the area of trapezoid ABCD equals to the sum of its two bases, that is to say AB plus DC, times the height over 2. The height must create 90 degrees with the two bases. So in trapezoid ABCD, AD is the height. Why? Because of the fact that AD creates 90 degrees with the base AB, this angle equals 90 degrees, and AD also creates 90 degrees with the other base DC. This angle also equals to 90 degrees. Therefore, the height is AD. So in total, we found out that the area of trapezoid ABCD equals to the sum of its two bases, that is AB plus DC, times the height, that is AD over 2. AB is x, DC is 7 over x, and AD is A. So in total, the area of trapezoid ABCD equals to x plus 7 over x times A over 2. But according to equation 1, we have already found out that x plus 7 over x equals to a plus b. So we can substitute x plus 7 over x by a plus b. We did it. So this is this x plus 7 over x is a plus b. So in total, this expression equals to a plus b times a over 2. Here we open the brackets and finally found out that a times a is a squared plus ab over 2. But a squared plus ab according to equation 2 equals to 14. Therefore, substitute a squared plus ab by 14. So in total, this expression equals to 14 over 2, that is 7. So in conclusion, we found out that the area of this trapezoid ABCD is equals to 7 square meters. We finished with the first question. The next step I actually presented to you the second question, and we solved the second question. mission is in the second question is to find out the area of this green shape. So in the drawing we have rectangle ABCD. We know that side CB of rectangle ABCD equals to 7 units. Inside rectangle ABCD we have, this is line segment CP that is equals to 4 units in its length. This is line segment PQ that is equals to 2 units in its length. This is line segment QA that is equal to 5 units in its length. This is angle CPQ that is a right angle, and this is angle PQA that is also a right angle. Again, our mission is to find out the area of this green shape. So first of all, we join point C and A together by a straight line. And we define the intersection point of diagonal CA of rectangle ABCD with line segment PQ, this point is point M. So we have here line segment PM. We define this line segment PM as X. So what is the length of line segment MQ? From the drawing it is very easy to see that MQ equals to PQ minus PM. MQ equals to PQ minus PM. So MQ equals to PQ, that is 2 according to what is given as the equation, minus PM, that is X according to our definition. So in total we actually found out that MQ, this line segment MQ equals to 2 minus X, and PM equals to X according to our definition. Okay, so here by doing this construction, by joining point C and A together by straight line, we can get here those two vertex angles, and we know that vertex angles are equal to each other. So if this vertex angle PMC equals to theta, then the other vertex angles, that is angle AMQ, must be also equal to theta. Then we focus on this right angle AQM. In this right angle AQM, this angle equals to theta. This angle equals to 90 degrees, and therefore the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees equals to 180 degrees. That is the sum of the angles in any triangle. According to the same logic, if you focus on this right small triangle PMC, this angle equals to theta. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. In the next step, we prove that those two right angles are similar to each other. That is to say that the right angle AQM, the right angle AQM is similar to the right green small triangle CPM. So why those two right angles are equal to each other? First of all, those two angles are both equal to theta, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the angles in the right angle AQM are correspondingly equal to all the three angles in the right green small triangle PCM. Therefore, we actually proved that those two right angles are similar to each other according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PM in the right angle PCM over side MQ in the right angle AQM is equal to side PC in the right triangle PCM over side AQ in the right triangle AQM. Okay, again we derive that PM over MQ equals to PC over AQ. PM is X, MQ is 2 minus X, PC is 4, and AQ is 5. So in total we found out that X over 2 minus X equals to 4 over 5, or 4/5. Here we first multiplied this equation, and finally found out that 5x equals to 4 times 2 minus x. Here we open the brackets on this side of the equation, and finally found out that 5x equals to 4 times 2 is 8 minus 4x. So 5x equals to 8 minus 4x. Here we added 4x to this equation, and finally found out that 4x plus 5x is 9x. So 9x equals to 8. Here we divided this equation by 9, and finally found out that x equals to 8 over 9, or x equals to 8 nines. So here, this is side PM, that is equal to x, and x equals to 8 nines. So what is the length of MQ? MQ equals to 2 minus x. But 2 is 18 ninths, so 2 minus x is 18 ninths minus x. And x is 8 ninths, so in total 2 minus x equals to 18 ninths minus 8 ninths. 18 ninths minus 8 ninths equals to 10 ninths. So in total, if you found out that MQ is equals to 2 minus x equals to 10 ninths, by PM is equal to x equals to 8 over 9. In the next step, I copied this line AQ PC in your page and analyze this line AQ PC. So actually, this is line AQ PC that I copied from the original drawing. AQ equals to 5, PQ equals to 2, PC equals to 4, this angle is right angle, and this angle is also right angle. In the next step, we extended the straight line AQ by straight line. When you extend the straight line by straight line, the result is the straight line. So this is the straight line. If you focus on the upper side of this straight line at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3 that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of this straight line at point Q? We have this angle, this is the right angle, plus the missing angle. In total, they must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we did a construction. That is to say, from point C, we drew perpendicular on the extended AQ. Again, from point C, we drew perpendicular on the extended AQ. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C in the extended AQ as N. By doing this construction, we created a quadrilateral PC and Q. Inside this quadrilateral PC and Q, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the 4th missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4th missing angle must be equal to 90 degrees in its size. So inside quadrilateral PC and Q, we have 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we relate to this quadrilateral PC and Q as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle PC and Q, side PC must be equal to the opposite side and QN. But PC is 4, therefore QN must be also equal to 4. Likewise, according to the same rule, in the same rectangle PC and Q, side PQ must be equal to the opposite side CN. But PQ is 2, therefore CN must be also equal to 2. In the next step, we join points A and C together by straight line. By joining points A and C, we created the right triangle, triangle ACN. In the next step, we implemented the Pythagoras theorem on this right triangle ACN. According to the Pythagoras theorem, in this right triangle ACN, AC square equals to CN square plus NC square. Again, AC square equals to CN square plus AN square. So AC square equals to CN square. CN is 2, therefore CN square is 2 squared, that is 4. Plus AN square. AN in total equals to 5 plus 4, that is 9. So AN square is 9 squared, that is 81. So in total, AC square equals to 4 plus 81, that is 85. So AC square equals to 85. It is given us the question that A, B, C, D is a rectangle. We know that the opposite sides in any rectangle, all the angles in any rectangle are right angles. So this angle, angle ABCD, this is angle ABC, that is a right angle. In the next step, I copied this right big triangle ABC in the new page, and we implemented the Pythagoras theorem on this right big triangle ABC. This is the right big triangle ABC that I copied from the original drawing. It is given as the equation that side CB equals to 7, and AC square equals to 85. According to what we have already found out, here AC square equals to 85. So according to Pythagoras theorem, in the right triangle ACN, AC square equals to AB square plus CB square. Again, AC square equals to AB square plus CB square. AC square is 85, and it is equals to AB square plus CB square. CB is 7, so of course CB square is 7 squared, that is 49. Here subtract the 49 from this equation, and finally found out that AB squared equals to 85 minus 49 is 36. So AB squared equals to 36. We took a root out of this equation and finally found out that AB equals to 6. This is side AB, this is equals to 6 units in its length. Our mission is to find out the area of this green shape. So what is the area of the green shape? The area of the green shape equals to the area of the right big triangle ABC. But because of the fact that the area of the right big triangle ABC includes also the area of the white triangle AMQ, and interested only in the green area, we have to subtract from the area of triangle ABC the area of the right triangle AMQ. And because of the fact that the area of triangle ABC doesn't include the area of this green small triangle PCM, we have to add to the area of triangle ABC the area of the green small triangle PCM. So in total we actually found out that the area of the green shape equals to the area of the right big triangle ABC minus the area of the white right triangle AQM plus the area of the right green small triangle PMC. Again, the area of the green shape equals to the area of the big right triangle ABC minus the area of this the area of this white right triangle AMQ plus the area of this green small right triangle PCM. Okay, so the area of the triangle ABC equals to the base that is AB times the height to the base that is CB over 2. The area of the white right triangle AMQ equals to the base that is AM times the height that is MQ over 2. The base AQ times MQ over 2. Plus the area of this green small triangle PCM. The area of this green small triangle PCM equals to the base that is PC times the height that is PM over 2. Repeat again, the area of the green small right triangle PMC equals to the base that is PC times the height that is PM over 2. So here AB is 6, CB is 7 over 2. 6 times 7 over 2 is 21. So the area of the right triangle ABC is 21 square units. Minus the area of the right green triangle AMQ. The area of the right green triangle AMQ equals to AQ, that is 5, times QM, that is 10/9 over 2. Plus the area of the green small right triangle PMC, that is equals to PC is 4, PM is 8/9 over 2. So the area of the green shape in total equals to 21, that is the area of triangle ABC. And this expression equals to, in total, to 25 minus 25 over 9 plus the area of the green small triangle PMC, that is 16 over 9. So in total the area of the green shape equals to 21 minus 25 over 9 plus 16 over 9. So it is 21, and here minus 25 plus 16 is 9, so this expression equals to, in total, to minus 9 over 9. So the area of the green shape equals to 21 minus 9 over 9. Minus 9 over 9 is minus 1, so in total the area of the green shape equals to 21 minus 1, that is 20. In conclusion, I actually found out that the area of this green shape is equals to 20 square units. Okay, thank you very much.